So students, last video we left off with the promise this exact scale runs inside stuff you already own. Today we are caching that in. We are going to zoom all the way out and look at real pipeline that turns your Verilog code into an actual chip sitting inside a phone, a car, a PS5, wherever. This is basically the how it's made. This quick recap on where this skill lands you because it's honestly will how spread out it is. CPU and GPUs, the brains of every laptop and console. Mobile chips, literally the SoCs, system on chip inside your phone right now. Automotive, EV control units, self-driving hardware, IoT, the chip inside your smart speaker. Telecom, the silicon that physically carrying 5G. Gaming, custom silicon inside PS5 and Xbox. It's like learning to drive. You don't just learn car. That one skill unlocks Uber, road trips, moving apartments, literally everything. Verilog is the same. One skill plugged into six completely different industries. So, how does a company actually go from we need a chip to here's a physical chip? This is the VLSI design flow and it's basically a relay race. Every stage hands off to the next and nobody skips a leg. Before any code, there is a specification. Think of like an architect brief. We need a chip that does X, runs at Y speed, uses Z power. No Verilog yet, just requirement. Step 2, RTL design. This is where Verilog comes in. Engineers write RTL, register transfer level code, describing exactly how data moves and gets processed. This is your gate level data flow and behavioral modeling all showing up here for real. Functional verification. Before anyone trusts this code, it gets stressed, tested, test benches, simulations, edge cases, the whole Unit 5 toolkit. Think of this like crash testing a car. Before it's sold, you don't find out it fails on the highway. Next stage is synthesis. A tool takes your RTL and converts it into an actual gate level netlist. Real AND gates or gate flip-flops. This is the moment your code stops being code and starts being circuit. Next is physical design, place and route. Now those gates need actual physical position and wiring on the chip. It's like city planning, deciding where every building goes and how the road connects, except the roads are microscopic copper wires. Stage 6, that is verification again, static timing DRC LBS. Yes, more checking. Does the chip meet timing? Does the physical layout match the design rules? This is the final inspection before. Stage 7, tape out and fabrication. Tape out, the design gets sent to a foundry like TSMC or Intel to actually be manufactured on silicon wafer. Once this happens, there is no more editing. It's baked in literally. Real quick, because you are probably wondering, okay, so what job do I get? RTL Designer Engineer writes the code, Verification Engineer breaks the design on purpose before it breaks for real. Stage number 3, Physical Design Engineer, the city planner. Stage number 5, DFT Design for Testing Engineer makes sure the chip can be tested after it's manufactured. Every single one of these rows touches what you have learning in this playlist. This isn't just an academic exercise, this is literally the job. So that's the full loop specification, RTL verification, verify, synthesize, physical, tape out, and chip. An actual chip in someone's pocket. Every unit in this playlist maps onto stage 2 and 3, the part where you come in. Next video, we go back to basic and start unit number 1 for real levels for design abstraction, the different ways you can describe the exact same circuit. Subscribe, stay in the playlist. Let's keep building. Thanks for watching.